Hello everyone, welcome to the 37th lecture in the series. In this lecture, we are going to learn about the greedy approach to problem solving. We are going to see how this greedy approach can be used to solve the knapsack problem. There are different types of knapsack problem and the greedy approach cannot be applied to all the types of knapsack problem. Specifically, we can apply greedy approach for solving fractional knapsack problem. So, I will be explaining you first what greedy approach is and to what classes of problems we could apply this greedy approach to problem solving. Then I would be explaining you the knapsack problem in detail and its types. Then we will be seeing some of the examples and how this greedy approach actually applies to solving this fractional knapsack problem. So, first let us see what greedy algorithm is. So, it is one of the problem solving approaches and we could use this greedy approach for solving any sort of meta heuristic problems, and the motto behind greedy approach is that we will be using we will be looking for only the locally optimal solution at every point of time, and we hope that by choosing this locally optimal solution at every step, ultimately that will help you to find the global optimum. So, in greedy approach we do not stop with getting a solution to the problem, rather we make every attempt and to find the globally optimal solution. So, there are different kinds of problems actually, and the solutions for solving the different problems are broadly categorized into two classes. Certain classes of problems we call them as class P problem and certain other we call them as class NP. So, class P problems could be solved with polynomial time, and there are certain other problems which fall under class NP, and for class NP problems not every problem will have a solution that could be solved in polynomial time. So, here this greedy approach could be primarily used for satisfactory problems for which there is no specific algorithm designed to solve it, and in specific we can apply this greedy approach for combinatorial optimization problems. So, in combinatorial optimization problems, those problems will have an optimization function, and our objective would be to either maximize or minimize this optimization function upon looking into some of the constraints. So, we should fit into those constraints and also we should see to optimize that function, either we may have to maximize it or minimize it. Say for instance, I could say that if the optimization function is something on profit, then we may be able to maximize the profit. At times it could be something on loss, in that case we may have to minimize the loss. So, depending upon the function we may have to either minimize or maximize it, and not only that we may have to see that we satisfy those constraints too. So, an optimization problem is a problem that involves searching through a set of configurations. So, this problem will have certain configurations. Of course, in one of the later slides I will be telling you what configuration is, and our objective would be to either minimize or maximize the objective function that is set for those configuration. So, in this greedy approach to problem solving, we apply this greedy approach to this optimization problem. So, we will be looking at the set of feasible solutions for that problem, and at any point of time we will be picking one of the solutions as feasible one compared to others, and we do not stop with that solution, rather we greed for getting even more better solution at further stages. So, here the thing with greedy approach is that we start from the sequence. We will have some initial configuration or a starting configuration, and then upon successive iterations we will be making some decision that is best at that point of time, and probably we may have to revise the decision if at later iterations we are getting some other better solution to the problem. So, this is how your greedy approach actually works. We start with some initial configuration, and initially upon looking at a local maxima we take that as the solution at that particular iteration, and after that we continue with, and at times we may be finding some other global optimal solution later at some other iterations. So, we always pick up the choice that looks best at the particular moment or a particular iteration, and we make a locally optimal choice, and we believe that this locally optimal choice will ultimately lead us to some other globally optimal solution. So, we call this as greedy choice property. So, for any optimization problem, if we adopt this greedy approach to problem solving, we stick on to this greedy choice property. The greedy choice property is that we choose some other locally optimal solution at one point of time, and we may even revise it later at some of the iterations if we end up with some other globally optimal solution. So, the greedy approach does not always guarantee us an optimal solution, and the problems that have a greedy solution usually possess this greedy choice property which I explained before, and this greedy approach can be used to classes of problems which are meant as hard. Hard problems means they cannot be solved in polynomial time, and for those problems we generally try to provide an approximate solution for that problem. So, this greedy approach is predominantly applicable to problems which are termed to be hard, and for those problems we generally look for approximate solution than looking at exact solution. So, these are some of the things that need to be possessed by a problem if we are going to adopt this greedy approach to problem solving. As such, it is one of the problem solving paradigms. So, this greedy approach is built on certain elements. The very first element is configuration. So, in one of the earlier slides I was mentioning this, for a problem to be solved using greedy approach, we need to have a configuration. It could be different choices or having collections or different values that we want to find. And for that problem we have to set up an objective function, and this objective function will have a score assigned to that configuration that we set up in the previous step, and our objective would be to either minimize or maximize that configuration that is set up. And this greedy approach works best when applied to problems that satisfy the greedy choice property, and I told you what this greedy choice property is. So, we choose a locally optimal solution believing that it will ultimately lead us to a globally optimal solution. So, we will be starting with some initial configuration. At every iteration we will be doing some sort of local improvements in an attempt to find a globally optimal solution, and that is what we mean as greedy choice property. So, in this particular slide I have given you a comparison of the dynamic programming approach to problem solving and greedy approach to problem solving, and of course, in some of the earlier lectures we have already learnt what dynamic programming is, and we have even solved two problems using this greedy approach before, especially with the traveling salesman problem, etc., and shortest path. And so, here with dynamic programming as well as with greedy approach to problem solving, both are applicable for problems that have an optimal substructure. So, optimal substructure in that sense, we can get an optimal solution to a problem only if there is a possibility of having optimal solution to all of its sub problems, and that is what we mean as the problem is having an optimal substructure. And in dynamic programming we can make an informed choice only after getting optimal solution to all the sub problems, whereas with greedy approach to problem solving we will be taking a greedy step or greedy choice before solving the sub problem. So, whatever looks best at that point of time we will be fixing it or choosing it, and this dynamic programming approach is dependent or particular approach. There will be sub problems that are all overlapping in nature, whereas in case of greedy approach those sub problems are not at all overlapping. So, at every iteration or round we will be selecting only one sub problem, and the sub problem size will be decreasing thereafter. So, this is one of the differences between the dynamic programming approach and the greedy approach. So, this greedy approach, as I said before, first and foremost we may have to cause the optimization problem, then we have to verify or demonstrate that it contains an optimal substructure, which means we will be combining the optimal solution to all the sub problems via the greedy approach with an assumption that that will lead to a globally optimal solution to the original problem. And we try to prove that there is always an optimal solution to the original problem by taking this sticking on to this greedy choice property. So, to yield an optimal solution, these greedy algorithms usually expect the problem to possess the following things. One is the optimal substructure property, which we say that an optimal solution to the problem contains within it optimal solution to all of its subproblems, and we also say that it should satisfy the greedy choice property, and making locally optimal choices will ultimately lead us to a globally optimal solution. These are certain examples of problems for which we can apply this greedy approach to problem solving. First is the vehicle routing problem. So, what that problem is that consider that we have goods that have to be moved from one point to another point, and our objective is to find the optimal route the vehicle should take in order to fetch the items from the pickup point and to deliver the same to all the drop off locations. So, it is much like starting at one point and reaching up all the drop off locations, and that too with the cheapest path. And another class of problem is the traveling salesman problem, which we have learned before. We will be having a list of cities and distances between them, and the objective of the traveling salesman is to reach out to all the cities via the shortest possible path. And not only that, he should be visiting every city exactly once. So, that is what we call as the traveling salesman problem, which we learnt in one of the earlier lectures, and for that problem we proposed a solution via the greedy approach. And there is another class of problem called as coin change, where the objective is to issue change with minimum number of coins for a particular denomination. And we with this lecture we are learning the knapsack problem, and not only that, for even shortest path problem also we can apply this greedy approach to problem solving. So, now let us see what this knapsack problem is. So, knapsack problem, it is a kind of combinatorial optimization problem. So, here we will be having an objective function, and we may have to either maximize or minimize it. So, this knapsack problem derives the name from following the maximization problem of the best choice of essentials that can fit into a bag when we think of going for a trip. So, we are having a bag and we are thinking of packing up items onto that bag in such a way that we do not exceed the bag's capacity, but what are all the items we carry on that bag should have some weight and value, and our objective is to maximize the value or profit of the items taking on that bag without exceeding the bag's capacity. So, given a set of items and those items having weight and a value associated with it, we are supposed to determine the number of each item to include within that bag in such a way that we do not exceed the bag's capacity. But at the same time we may have to maximize the total value, and maximizing total value in that sense we are taking up those items whose value or utility would be more without exceeding the bag's capacity. So, that is what we call as the knapsack problem. So, here I have put up the problem in simpler terms. We have a bag, the bag's capacity is 15 kg, and we are given it up with some items. So, with every item we have its weight and we have its value or profit. So, here let us consider this blue object, its weight is 2 kilograms and its value is $2. and when you sum up all the weights, you could see that the total weight is 20 kilograms, which means that we are exceeding the bag's capacity, and our objective here is to take maximum items of good utility or value and not exceeding the bag's capacity. So, here the goal is to determine the number of every item to include in that collection, so that the total cost is less than the given cost and the total value is as large as possible. And there are different kinds of knapsack problem. We say that there are 3 types. One is the 0 bar 1 knapsack problem. The 0 bar 1 knapsack problem is one where you can take up an item either as a full or nothing. So, we can't take only a fraction of an item, either the item should be taken up as full or we do not take that item or we drop that item, right. And so, the name is 0 or 1. So, it restricts the number of each kind of item to either 0 and 1. Another class of knapsack problem is bounded knapsack problem. Here what we do is that there is a boundary set up for every item. So, there is a restriction on the number of each item to a specific value. And there is another class of knapsack problem which we call as unbounded knapsack problem, where there is no boundary on the number of each item. So, when you look at the complexity, the general knapsack problem is said to be NP hard, which means those class of problems cannot be solved within polynomial time, or in other words I could say that there is no known algorithm to solve those problems within polynomial time. So, for this class of problems we generally provide approximate solution, and for providing those approximate solution we could use the greedy heuristics. So, here is an example for 0 bar 1 knapsack problem. This problem is put up in simpler terms with an example here. Let us assume that the person named John wishes to take n number of items for his trip, and as such every item has a weight associated with it. If I is the item, then its weight is Wi, and items are all different. The items to be carried in the knapsack has a capacity or a weight associated with it, which is C here. And when the sum of all the item weights is less than or equal to C, then there is no worry at all. We can take up all those items within that bag or the knapsack. When the sum of all the items weights is greater than C, then we may have to fix up, or we may have to decide which are all the items that have to be put up within the knapsack and which are all the items that have to be dropped and left behind. So, here in our case we are having plenty of choices which we call as items, and every item has an weight associated with it. This is our knapsack which has a capacity associated with it. So, here now John assigns a profit Pi to every item, and whatever weights those items contain and whatever profit this John assigns to that item, they are all positive numbers. Now, John wants to select a subset of items which can be put up within that knapsack, and for that there are certain constraints. The first constraint is the weight of the subset of items which John decides to put it within the knapsack should not exceed the total capacity of the knapsack. The second constraint is that John can't take only a fraction of an item within the knapsack. Say for instance, if there is a jam bottle to be considered as an item, and if its value is something and its profit is some other value, say y, then if in case by putting that jam bottle within the knapsack we are exceeding the capacity, then John cannot make a decision as to take only a fraction of that item. That is what we say here as one of the constraints. And the third thing is that the profit of the subset is calculated as the sum of profits of all the items that are selected to be placed within the knapsack, and that is our optimization function. and we are supposed to maximize this optimization function here just because it is a profit, and the profit of the selected subset should be the maximum one, and that will be taken up as the solution for the problem, and that is going to be our optimization criterion here. So, let us consider that when xi is equal to 1, which means the particular item is selected, and when xi is equal to 0, it means the particular item is not considered for putting up within the knapsack, and hence this particular problem has been given the name as 0 or 1 and knapsack problem. And of course, for this for solving this kind of problem, we cannot use the greedy approach. Just because it is one of the types of knapsack problem, I just wanted you to know what this 0 bar 1 knapsack problem is. And this particular problem is usually solved with dynamic programming approach, and of course, the focus of this lecture is to solve this knapsack problem using greedy approach. So, we are going to learn another class of knapsack problem called as fractional knapsack problem, where we apply this greedy approach. So, when we make an attempt to solve this 0 bar 1 knapsack problem with this greedy approach, so we may have to do a greedy attempt on utilizing the maximal capacity. So, the greedy criterion is that we select the items in the increasing order of weight. So, let us assume that we have 2 items where n is equal to 2 and the capacity of the knapsack is 7, and let us consider that we have 2 items and those items weight are 3 and 6, and associated profit is 2 and 10, which means the first item's profit is 2 and the second item's profit is 10. If in case I make a choice to choose the first item, then its weight is 3. So, if I put it within the knapsack, then I will be having only 4 weights left behind, and of course, I may not pick up the second item then. So, if only first item is selected, then the profit that I would get is only 2, and so we say that this is not the best solution, because there is one other item whose profit is 10. So, this choice of taking the first item is not the best selection or the solution. So, if we make a greedy attempt on profit earned, so in that case what we have to do is we have to select the items in decreasing order of profit. And so, let us consider for an example, we have 3 items and the capacity is 7 and the weights of those items are 7, 3 and 2, and those 3 items have a profit associated with them, which are 10, 8 and 6. So, if in this case our greedy criterion is selecting the items in decreasing order of profit. So, I choose the first item. If the first item is selected, then the profit is 10, but of course, it is not the best selection, right. So, because of these constraints, we do not apply this greedy approach for 0 bar 1 knapsack problem. So, now let us see what this fractional knapsack problem is. So, consider that we have a set of items and that set contains n number of items, and each of those item has a benefit value associated with it. Whatever we have been mentioning as profit before is what I say as benefit now, and every item has a weight associated with it, which is Wi, and the goal here is the same. We want to choose the items with maximum total benefit value, but with weight at most capital W, where capital W is the maximum weight that could be carried on this knapsack. So, if we are allowed to take only a fractional item amount of every item, then this problem is called as a fractional knapsack problem. So, let us assume that we have taken up the item xi, and we want to we will be taking a fractional portion of the item every time we exceed the capacity. We check that we do not exceed the total capacity of the knapsack. So, we write the objective function now as it is summation of bi into xi slash wi, where xi is every item and wi is the weight associated with it. So, we are taking only a fractional portion of that item, that is what we mean as xi slash wi, and we are just computing how much of benefit is associated with the fraction that we have considered now. and our objective is to maximize this profit or the benefit. But we have certain constraint that we take up a set of items and we sum up all of its weights, and those weights should not exceed capital W, which is the capacity of the knapsack. So, here in order to better understand the fractional knapsack problem, we have given a simple example here. We have the same set of n items, and every item is having a benefit associated with it and a weight associated with it, and both benefit as well as weight are positive numbers. And our goal is to choose items with maximum total benefit, but with the total weight of all those items not exceeding the total capacity of the knapsack, which is capital W. So, here this is our knapsack and our capacity is 10 ml, and I have different items each having a weight as well as some benefit associated with it. And so, here what we do is that we say this as the solution for the knapsack. We are not taking any item to its full, rather we take a fractional portion of every item, and say here I have taken up 4 items and all those items are taken in fractional amounts in such a way that we do not exceed the total capacity of the knapsack. So, in fractional knapsack problem, what we learn is that we are having a set of items and each having a benefit and a weight associated with it, and we want to maximize the benefit in such a way that we do not exceed the total weight of the knapsack. So, here this is what the objective function that we set up. One is that the objective function is that we take only a fraction of that item, and that fraction is denoted by xi/wi, and we multiply that with benefit, and we take the collective benefit, and the reason for doing a summation here is that we want to maximize the benefit. And we have a constraint also written for this problem. The constraint is that we do not exceed the total capacity of the knapsack. So, whatever items and their fractional parts we have taken up, we sum it up and we check with that we do not exceed the total weight of the knapsack. So, this is the algorithm for fractional knapsack problem. We have a set of items with the benefit and weight, and we are given up with the total capacity of the knapsack, and our output would be like we are going to take some fractional amount from every item that maximize the total benefit while not exceeding the capacity of the knapsack. So, every time we pick up an item from the set, what we do is that we assume that the item taken is 0 initially, and we compute the value index for every item which is bi by wi, and initially the total weight is initialized to 0, and every time we check that this small w is lesser than the capital W, which is the total weight of the knapsack or total capacity of the knapsack. We remove an item with highest value index at that particular point of time from the set, because we are using a greedy approach. So, we always make a greedy choice at every step. So, we remove the item with the highest value index. Then we check whether that particular item could be added to the knapsack. For that, what we do is that we check its weight and we compare whatever the remaining weight with the knapsack. So, the weight of the item is wi, the leftover weight in the knapsack is w minus w. In our case, initially our small w is 0 by the time the knapsack is empty. So, capital W is the maximal capacity of the knapsack, and that is our A, and then we assign A to xi, that is going to be the fractional amount we are going to take from item xi, and we add that value A to small w. So, during the next iteration we check now whether the w is less than the capital W. If so, we proceed with successive iterations of adding more items into the knapsack. So, here with fractional knapsack problem, the greedy choice that we make up during every iteration is that at every point of time we try to take up an item whose value benefit is more, and with the objective that we want to maximize the benefit. So, as given here, we take up an item, we compute its value benefit, and then we initialize small w to 0 initially, and we check whether we do not exceed the knapsack's capacity, remove the item with highest benefit value, check whether it could be added up to the knapsack. If there is a space in the knapsack, we add it up, and we continue doing this till we could add more and more of items into the knapsack without exceeding its capacity. So, when you look at the running time of this fractional knapsack problem, so we need to maintain a heap. As you know, we have a collection of items having benefit and weight associated with it, and our objective is to maximize the benefit by taking fractional amounts of every item in such a way that we do not exceed the total capacity. And for this particular algorithm, the running time is order of n into log n. So, for storing all of those items, we can use a heap based priority queue, and removal of every item from the heap based priority queue would require a time complexity of order of log n. And so, for if we are to add up n number of items, then it is going to be n into log n. Only in the worst case, this algorithm would make us to add or remove all the items from the heap. So, in order to verify the correctness of this problem, what we could do is that suppose let us assume that there is a better solution. There is an item I with a higher value than the chosen item j, but item i's weight is xi is less than wi and xj is greater than 0, and value of item I is less than value of item j. If we substitute some other I with j, then we are getting a better solution. So, we need to find how much of I has to be taken by doing this comparison, that is minimum of wi minus xi and xj. We compare these two and we are fetching the minimum of this, but we will not be able to find better item just because we are adopting a greedy strategy at every point of time. At every whenever we are making a choice, we are making a greedy choice, which means we are taking the item only whose value benefit is more. So, this is not at all feasible here. And as I said, for implementation sake, we will be using a heap based priority queue for storing up all the items along with their value and weight. And with the priority queue, we make a greedy choice every time, and we always remove an item from the heap based priority queue which has a greatest value index. The value index is what we computed by dividing the value of the item with its weight, and for using this priority queue based implementation, we need a time complexity of order of log n. So, in total, this fractional knapsack algorithm can be implemented in order of n into log n. And this fractional knapsack problem always satisfies the greedy choice property which we learned before, and its time complexity is going to be order of n into log n. So, to summarize what we have seen so far, we learned what a greedy approach to problem solving is, and we learned how this greedy approach could be used for solving the fractional knapsack problem. In a fractional knapsack problem, we are not taking an item to its full, rather we are taking a fractional portion of every item and we are picking up the item whose value benefit is more. And here, before we start this approach, what we do is we sort all the items according to their value to weight ratio, and we sort them in decreasing order, and we choose the item with the most valuable weight ratio. And in order to fetch items and keep on adding it to the knapsack, we use a priority queue. It is a heap based priority queue, and we are adding the items to the knapsack starting from the item with the highest value weight ratio, and we will be keeping on adding the items into a knapsack until we do not exceed its capacity. If suppose an item does not fit fully, then this fractional knapsack problem gives us the liberty to take only a fraction of that item without exceeding the capacity. And as such, the time complexity of this knapsack problem using the greedy approach is order of n into log n, just because first we do a sorting of n elements according to their value weight ratio, and then we remove the items one after the other using a heap based priority queue. So, we say that its complexity is n into log n, and this greedy approach is not optimal for solving the 0 bar 1 knapsack problem. In general, we solve that 0 bar 1 knapsack problem using dynamic programming. So, to check whether we have understood the concepts of knapsack problem and the greedy approach better, let us have some review questions here. The first question is, what is the main difference between 0 bar 1 knapsack and the fractional knapsack problem? As I said, both are two types of knapsack problems usually have, and in 0 bar 1 knapsack we always take an item either on its as a full item, or we do not take that item if we feel that the particular item's weight exceeds the capacity of the knapsack. Whereas in case of fractional knapsack problem, if by taking an item we see that the knapsack capacity is exceeded, then what we do is that we do not try to take up the item to its full, rather we take only a fractional portion of that item. And why does the greedy approach work well for fractional knapsack but not the 0 bar 1 knapsack? So, here in greedy approach we always make a locally optimal solution at every step, but in case of 0 bar 1 knapsack, if we do so, then we may have to think of dropping an item back without putting it in the knapsack, just because it gives us, it insists that the item can be either taken as full or not. But in case of fractional, that is not necessary, and so greedy approach is best suited for fractional knapsack problem. What is the strategy used in greedy approach for solving the fractional knapsack problem? The strategy is that we first compute the value weight ratio for every item, and then we sort the items according to their value weight ratio in decreasing order, and every time we pick up or we start adding the items to the knapsack by looking at items whose value weight ratio is more, right. So, that is what the strategy we adopt for solving this fractional knapsack problem. And what is the time complexity of this greedy algorithm for fractional knapsack problem and why? You know, the fractional knapsack problem has a time complexity of order of n into log n, where n is meant for sorting up the items according to their value weight ratio, and as we are using a heap based priority queue, every time we remove an element from the heap, the time complexity is order of log n, and so the total complexity is order of n into log n. Can sorting by weight instead of value to weight ratio will give an optimal solution for the fractional knapsack? No. Here the speciality of fractional knapsack problem is that it gives the flexibility to take an item in fractions. So, we have to compute the value to weight ratio, and that only helps to make an optimal choice at every step, and so sorting by weight will not help us to get a better solution than sticking on to value to weight ratio. So, hope you have understood the concept of greedy approach as well as the knapsack problem, and specifically how this greedy approach could be used for fractional knapsack problem. And